What's up, guys? This is Mr. O'Brien. This is going to be part 3 of the lecture series Formation of Covalent Bonds, Unit 2C. The information that I will talk about today is in section 9.5, and it deals with polarity. Okay, so at this stage, you got to make sure that you know how to draw the electron dot structures, and and be very competent in knowing the molecular shapes. If you don't know molecular shapes, go back to part 2 of my lecture series that will teach you more about the molecular shapes. All right, so let's go ahead and start talking about this. So do all nonmetals share equally in covalent bonding? Now remember, the key word here is covalent in sharing. But the question is, do they share equally? Now take a look at these two pictures in these two situations. Here you got two girls, sharing a pizza and maybe watching a chick flick or something. And here you have a father and a son sharing a pizza as well. Maybe they're watching Avengers. Who knows, right? But do you notice, or could you comment on the differences of how they share the pizza? Now, what would you expect? Would you expect that the sharing here happens equally and the sharing here happens unequally, right? Now, why would the sharing here look like it's unequal, but here it is equal? And it's not because the dad's mean to his son. It's just because the nature of who they are, right? The son probably is attracted to a little bit of the pizza. He's not that hungry. Little kids aren't always hungry. They're always down to play. But us adults, as we age, we like to eat more and more and more. So the nature of who we are allows for us to kind of dictate if we're going to share equally or unequally. So let's see how this relates to bonding. Well, the amount of sharing that exists between the two nonmetal atoms is really based on the difference of electronegativity, right? And if we're looking at this chart here for electronegativity, and it's a number chart, not that you're going to have to know the numbers, but we can tell that the nonmetals, which are in yellow, right, have all high electronegativity values relative to the metals. And that's why these guys share electrons. But how do they share electrons? Do they share electrons like this, where one of the atoms here pulls equally on the other atom, right? Or does it share kind of unequally here, where one of the atoms, right, has a greater pull, right, on the electrons than the other atom? Now, not saying that the atom doesn't have any attraction towards the electrons, not at all, because you see these kids want to play tug of war, right? But their attraction is not as great as their attraction is, so hence they need to share. And this attraction here is almost the same because they're not going anywhere, right? How do we identify that based on the combinations and the pairs of the atoms in a covalent bond? So we'll start talking about this some more. So there's some important terms that you need to recognize, and one of those terms is called nonpolar versus polar. And the idea of polar is that there is clearly an opposite, and that opposite that exists creates an unequal sharing of electrons, creating a polarity, a charge in the molecule, which we'll talk about later on. When something is nonpolar, there is no opposites because sharing is happening equally, right? And because there's no opposites, there's going to be no charges. Now, it might be weird to say charges, right? Because we've learned about charges when we talked about ionic bonds. But in ionic bonds, one steals an electron, recall, and creates a negative charge, and one loses electrons because one has no attraction to an electron, and the other one has a greater attraction. It's like kind of saying, like, if you bring a pizza between these two guys, this guy loves pizza, but this guy, I don't know, likes hamburgers instead of pizza, you see? So he won't have any of the pizza. But in this case here, the sharing occurs, right? Because as you can see, they overlap, right, for both of them. But the overlap is different. We have more electrons situated on this side than we do here. But here we have the same distribution of electrons, right? This distribution of electrons is because the electronegativity between the two is the same. Here, the electronegativity is different. And so because it's different, it creates what we identify as something called a partial charge. Okay? Now, you just have to recognize that small differences of electronegativity create this differences of charges versus no differences of electronegativities create no differences. And so hence there is no, it's equal on both sides, nonpolar. Now in your textbook, there are these kind of boundaries, limits between the electronegativities that you will not be required to know. I'm just trying to do the basics here, right? So what happens when atoms with different electronegativities that also have high electronegativities occur? Well, they create something we call a dipole, which is essentially a molecule that has a negative and a positive. It has two poles, right? Positive and negative. And so in this example here, I'm showing you where hydrogen hooks up with chlorine. And chlorine is more attractive than hydrogen, not because the numbers are here. Forget that. It's more attractive because it's a halogen, right? Remember that? The halogens, one more 7 valence electrons, one more valence electron needed to be a noble gas. So what ends up happening is that chlorine, because it's more attractive, it pulls the electron closer to itself, hence the dipole sign. Now you can even see there's more density of electrons here, right? Of valence electrons here than there is here because of that electronegativity difference. Now, what we do is we identify the charges with these small little delta signs. We don't give them a full plus and a full minus, but rather these small little delta signs. And these deltas indicate that, hey, there's an unbalance of charges here somewhere. And in this side, there's more of a negative field towards it. And this side is more of a positive field towards it because it's got less of the electrons. And this is called then a polar covalent bond. But in this case here, when you have two chlorine atoms together, this is going to be called a nonpolar covalent bond. This is called a nonpolar covalent bond because the electrons in this case are being shared equally because none of them have more power to pull the electrons closer to itself. So with that said, let me give you an example. So let's take a look at carbon and oxygen. So carbon's here and oxygen's here. What can we say about the bonding? Well, we know that the bonding is covalent. Okay? So we draw a line between the two. But how is this covalent occurring? Is it sharing equally or unequally? Well, we know that if there's a difference, even a relative small difference, then there's going to be some unequal sharing occurring. So in this bond, we identify this as O having a slight negative and C having a slight positive. We call this a polar covalent bond. Sodium and oxygen, that's a different story because sodium has a really low electronegativity and oxygen has a really high one. So they don't even share. Remember, they create ions. And these ions steal and lose electrons. So this is not part of covalent bonds, right? Big difference. But here, for O and O, they are nonmetals. They both have electronegativity. But negativity between them is really, really the same. It's nothing, right? There's no difference. And so we call this a nonpolar covalent bond. Okay? So consider, right? Consider these, consider these problems out and try them out. And if you have a hard time with these problems, hit me up at tutorial. We'll move on. So can a molecule exhibit dipole quality? So we've been talking about bonds so far, and the answer is yes. And it really depends on what we see as symmetry. If you don't know what the word symmetry means that if you cut an object in half and on the axis both sides are equal, we call it symmetric. But if it's not equal, we would call it asymmetric. Any ideas which one would be polar or nonpolar? Yeah, this would be nonpolar, right? And this would be polar. And why would it be regarded as polar? Because there's an opposite. There's an opposite here. There is no opposites here. So in order for you to see if a molecule has some sort of polarity, we're trying to find out charges, right? We got to see what the symmetry is all about. If the molecule is symmetrical, there's no polar, even if polar bonds exist. Take a look at this example. Here's carbon dioxide. You should know at this point that carbon dioxide has a linear shape. And you can see in the red that oxygen pulls the electron closer to itself than carbon does, because O is a little bit more attractive. So it has polar bonds. But the bonds between itself, right, do not create a polar molecule because A, there's symmetry. If you cut this in half, both sides are the same. Cut this in half, both sides are the same. There's no opposite in this molecule. Why, if you want to know? Well, the oxygen atom is pulling electrons closer to itself on this side. But that's being discounted with the same oxygen atom pulling electrons on that side. This is nonpolar. No charge. Now, water, however, is asymmetrical. It's not symmetrical at all. And as you can see here, how do we know that? Let's cut this in half. You can see an opposite. There's a difference here. There's more electrons on one side than there's the other. There's an opposite if you flip it the other way around. Notice, not this way, but in this case, right? So why is that? Well, again, there's polar bonds here. The O is pulling the electrons closer to itself. But because this molecule is a bent shape and not linear, it creates this asymmetric feel towards it. So hence we have the O as slightly negative, and the H's contain a slight positive side. So what happens if a molecule exhibits polarity? So if molecules exhibit polarity, then they're going to be affected by a magnetic field. Here's water, right, showing you the polar bonds between it. But the molecule itself is also polar. As you see, it's always going to be attracted, the positive ends, towards the negative side. Look at A and C. A and C is always attracted towards the negative side. And the B, which is the oxygen, which is the negative side towards it, is always attracted towards the positive end. But for CO2, because of the nonpolar nature of CO2, there's no attraction. It doesn't move. You can have C towards the negative side, you can have C towards the positive side, and nothing moves. And why does nothing move? Because again, there's an equal distribution of electrons. This has no affection, right, towards any charges, even though there's a polar bond going there and a polar bond, going there. There's no affection. Nonpolar overall. So try these problems regarding polarity for mastery. And if you have any questions on them, hit me up at tutorial. Thanks.